right, guys. I thought we had a really good first class yesterday. So I'm just going to go over a little bit about what we talked about so that nobody's confused. Okay, so you should have this student notebook already. I know some of you guys said you didn't have it and it's in the mail. So do the best you can without it, but I do expect you to do all the assignments even though you don't. So you'll need to be writing them on paper because I will be checking your homework assignments. So if you don't have these sheets, you need to have sheets that have your homework on them. I don't want you to not get credit for it just because you don't have your student notebook yet. But I am going to go over a little bit again about what I want you to do. I don't want you to have to lug this back and forth. And this is where you're going to take the sheets from this book. So I'm going to show you. It's full of these note sheets. This one has been completed, so just ignore that fact. But it's full of these note sheets. We're not going to be using those. If you want to use them, no problem. But you don't have to use those. So you're going to go to where it says Module 1, and it's got the on your own questions, and then it has the study guide questions, and then it has the practice problems, and it also has extra practice problems. So you're going to pull all of this. So right here, and then it goes to Module 2 notes. You are going to rip all of these pages out carefully, and then you're going to cut the little things off, hole punch it, and then you're going to put it into this section in your binder. And I want you to do this for the first 7 modules. So you're going to have this, then you're going to go to the Module 2 where it starts your questions right here, and you're going to do the same thing. You're going to go from this page to all through the extra practice problems because I want them there if you want to work on them. Up to here, you're going to rip it out, and then you're going to cut off the edge. You're going to hole punch it, and you're going to put it into this section of your binder so that if you were to look here, it's all the way through Module 7 in this binder. Okay, that's what we're trying to get through in the first semester. Okay, the second part that I want you to do is in the next tab, it says labs. You're going to do the same exact thing with all of the labs in the back of this student notebook. Okay, so if you go to the back of it, and let me see what page it starts on, I can show you. Okay, so it starts right here at 417, and you are going to do the same thing. So for the first 7 modules, because that's what we're trying to do in the first semester of Forge, is you're going to rip out these pages, you're going to cut this off, hole punch them, and then you're going to put them right here in your binder where it says labs. Okay? And then you're going to set this aside. You won't need this for the rest of the semester, but you will need it for the second semester when we do the same thing and add in the rest of them. Okay, so lab reports should have your rubric and the example I gave you. Quizzes, you don't have anything there yet. Tests, you don't have anything there yet, but that's where you'll put your graded tests. Then this is for labs, for in class. So when you're doing your reading, any lab that you read during your reading, you're going to go ahead and make your hypothesis before class, and then you're going to read over the lab. And then in class, when we're doing the experiment together, these are the pages you're going to take your notes on. So it's all in one location for you, okay? And then this section is going to have all those sheets. Okay, for this week, you are expected to do the on your own questions, all the on your own questions, the study questions, and the practice problems. If you would like to do the extra practice problems, you're welcome to, but I'm not requiring it. I will be checking this on Monday to make sure that you've done it. At the end of this video, because this is such a lot in 1 week, at the end of this video, I am going to work out the study questions and practice problems with you so that I kind of guide you along. So that will be at the end of this video. But I wanted to make sure that everybody's on the same page. Everybody understands what their setup in their binder looks like. And then those pages need to be in there. Again, for those of you that do not have your notebook yet, I will still be checking the section to make sure that you completed the on your own questions, the practice problems, and the study questions. So you're gonna have to have paper here that shows me that you completed those if you do not have this yet. Hopefully that makes sense. Let me know if you have any questions. Now I'm gonna finish the rest of the lecture since we ran out of time. All right, guys, we ran out of time, so I just wanted to talk a little bit about the rest of the module and kind of finish up the lecture. So I believe we left off at scientific notation. So on page 26, it gives you the 2 basic rules for using scientific notation in this chemistry course. Rule number 1 is you're going to place only 1 digit, not a 0, in front of the decimal point, okay? And rule number 2, only significant figures go in front of the multiplication sign. So anything you have here is considered significant, okay? And then they kind of work through some different examples. I'm gonna work through the problems at the end of this video for you, so hopefully you'll see what I mean by that. Another thing that I wanted to just remind you guys in the lecture are these 2 rules. We talked about them in class, but it's kind of a mouthful. But whenever you're adding and subtracting significant figures, your answer is going to have the same precision as the least precise number, okay? And when you're multiplying or dividing, your answer is going to have the same significant figures as the number that had the fewest significant figures, okay? And another thing I want to point out, so if we were doing this conversion right here that I have in my notes, 121 grams, if I were converting to kilograms, I would put this over 1, so I could do my conversion factor. I know in 1 kilogram, there's 1,000 grams. When you look at this problem, you might think, oh, okay, my final answer needs to have 1 significant figure, but that's not correct, okay? These numbers, the 1, and the 1,000, are not for measurements, but they're definitions. So they're considered to be infinitely precise, all right? So the 1 kilogram number, even though I have a 1 here, it would actually be 1.0000000000000. So you don't consider it when you're looking at the significant figures. You don't look at this 1, or this 1,000, okay? Because they're from definitions. They're not from measurements. Okay, hopefully that makes sense. We're not really gonna do experiment 1.3. You're welcome to look over that, but we're not going to do that right now. But we are going to jump into measuring temperature. Sorry, pass that up. Yeah, sorry about that. We are going to look at measuring temperature. Okay, so we need to discuss units of measurement when we're dealing with temperature. You're probably familiar with Fahrenheit, right? So when it's 20 degrees outside, 20 degrees Fahrenheit, you know you need to wear warmer clothing, right? Because it's cold. You also know if the weather said it was 200 degrees Fahrenheit, that's probably going to be a mistake, right? So in chemistry, we use one of 2 different units for temperature. You're either going to use Celsius or Kelvin. So you're going to become familiar with these units. You already know Fahrenheit, but we're not really going to use that. So you're going to become familiar with Celsius and Kelvin. So just talking a little bit about a thermometer. So a glass thermometer is composed of a tube that has a special liquid inside. And when you read a temperature, you're looking at how high that liquid rises or how low it falls as it expands and contracts within that tube. So the measurement is related to a temperature measure by a series of experimental steps. And then it talks about how you can calibrate a thermometer. Calibration is based on a fact that ice and water, if they're thoroughly mixed, the temperature of the mixture will stay the same. It will be 0 degrees Celsius or 32 degrees Fahrenheit, regardless of the amount of ice or water that's present. And then boiling water is always at the same temperature, which is 100 degrees Celsius or 212 degrees Fahrenheit. And that's all at standard atmospheric pressure. We'll talk about that a little bit later. Okay, so the important thing that you need to remember from this module right here is converting temperatures. So here is our formula. Degrees Celsius, that's going to be whatever temperature you have in Celsius, is equal to 5/9 the degrees Fahrenheit temperature minus 32. And you can rearrange that equation as needed whether you're going from Celsius and you need Fahrenheit, or you have Fahrenheit and you need Celsius, okay? Whichever way you can rearrange it. Okay, I'm not going to work through these examples because, again, I'm going to show you in just a little bit. And there's one more equation over here with temperature. Kelvin equals degrees Celsius plus 273.15. So that's another important equation for when converting temperatures. The precision of 273.15 is not exact, so it needs to be considered when determining significant figures, okay? Because you're adding, the numbers need to have the same precision as the least precise measurement in this calculation. So remember that moving forward. And then it talks about scientific law, the nature of scientific law, and the scientific method. So your book tells you, you know, how do you go from looking at materials all over the world to making statements about them, right? Like, how do you organize what you're learning about? You observe things, you make conclusions about them based on how they look, how they behave, things like that. You can notice whether a material is solid, whether it's liquid, whether it's gas. You can look at physical properties. Is it hard? Is it soft? Is it shiny? Right? So we know some materials like iron can rust. Other materials like gold cannot. So how do we classify and explain all of this, right? We ask questions, we perform experiments, we test those questions, we test our hypothesis, right? So we can make a hypothesis, an educated guess on what we think is going to happen to explain our observations. And then we do rigorous testing to test that hypothesis, right? And if over time, that hypothesis might become a theory, and then that theory might become a law. So a scientific law is an educated guess confirmed by lots and lots of testing. But if those tests are flawed, it is possible to have a scientific law that's incorrect, right? So we are going to use the scientific method in our experimentation throughout this course right here. Purpose, what's your goal, right? Hypothesis, what do you think is going to happen? Experimentation, you're going to test it with systematic observations, measurements, and technique. Analysis, you're going to determine whether the results of the experiment show or decide what actions to take, what did it prove. And then conclusion talks about what the results of the experiment show, and then your next actions to take after that. Okay, so this concludes module 1. So I know you guys read the whole thing. I lectured on it yesterday. This concludes our lecture. So now I'm going to jump in to working problems for you. Now I'm going to go over the practice problems and the study questions for you guys right now. So make sure you have your sheets and you follow along if you haven't worked the problems yourself, so you can do it now. And make sure you also have on your own. I do expect you to bring these pages with you on Monday to class so that I can see that you completed them as part of your homework. Okay. So starting with the study questions, number 1, which of the following contains no matter? That's going to be heat and light, right? Talked a little bit about that in class. Okay. Number 2, list the base metric units used to measure length, mass, time, and volume. So these were in that chart for you, but length, the base measurement for that is meter. For mass, it's going to be gram. Time is second, and volume is liter. And you just need to know that, okay? In the metric system, what does the prefix milli mean? Either one of these is acceptable, just like we talked about in class. It's either 1 over 1,000 or 0.001. Number 4, all conversion factors when in the form of a fraction must equal 1. Okay, number 5, which has more liquid, a glass holding 0.05 kiloliters or a glass holding 12,000 milliliters? You have to work this problem out. You're not going to just know. So 0.051 kiloliters, what is your conversion factor? Well, you know it is 1 kiloliter. There are 1,000 liters in 1 kiloliter. And then you multiply this out, cancel out your kiloliters, and you get 50 liters. If you have 12,000 milliliters Again, you know there's 1,000 milliliters in 1 liter, and you get 12 liters. So which one is more? Which one can hold more? That's going to be the first one. The glass holding 0.05 kiloliter has more liquid. I want to take a moment to tell you guys something. On your test, when you have problems like this, even if they're multiple choice, if this were to be a multiple choice question, which has more liquid? A glass holding 0.05 kiloliter, or B, a glass holding 12,000 milliliters. You must show me your work here and then choose your answer. I don't want you to just guess. I need to see that you actually worked out the problem. Okay? So even on multiple choice questions like this, make sure that you're showing me your work. All right, number 6. How long is the bar in the picture below? All right, they start here at the 1, so it's going to be 1, 2.5, and then you can see it's between the 6th and the 7th down there. And remember that your answer, your significant figures, is going to be 1 past the precision of your instrument. So I'm going to cut the corner and go halfway. So I'm going to say 2.65 centimeter. All right, number 7. 2 students measure the mass of an object that is known to be 50.0 grams. The first student measures the mass to be 49.8123 grams. The second measures the mass to be 50.1 grams. Which student was more precise? Which student was more accurate? Okay, so the answer is 50.0 grams. So the one that's going to be the most accurate is going to be the one that's the closest to the actual number. And that's going to be the second student, right? 50.1 is going to be closer than 49.8123. So the second student's more accurate. However, the first student is more precise. You see how many digits this goes out to? 49.8123 versus 0.1. So this one definitely has more precision to it. So the first student is more precise. Moving along. Okay. Question 8. Explain what a significant figure is. There are a lot of different ways that you can explain this. You do not have to have this exact wording, as long as you can tell me in your own words what it is. But it's basically a measured digit or number that comes from a measuring device or instrument. Okay. Number 9. How many significant figures are in the following number? A, 120350, or 120,350. Okay, remember in class we talked about all non-zeros are significant. So significant, 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 significant. This 0 is not going to be significant. It does not come to the right of the decimal at the end of the number or between 2 significant figures. However, this one does come between 2 significant figures. So that's going to be the 1, the 2, the 0, the 3, and the 5 are significant. So that's going to be 5. Okay, for B, how many significant figures in B? Well, again, the 1 and the 2 are going to be significant. Then you have the 0 on the end to the right of the decimal at the end of the number. And then the 2 other zeros are going to be significant because they're between 2 significant numbers, the 1 and the 2. So all 5 are going to be significant. And C, 0.00000012. All of those zeros are not significant. So it's just going to be the 1 and the 2. So 2 significant figures. And that's because those zeros don't come to the right of the decimal and at the end of the number, nor are they between 2 significant figures. And D, how many significant figures are there? You're going to have 3. The 7, the 2, and the zeros to the right of the decimal at the end of the number. So it's going to be 3 significant figures. Okay, 10. A student measures the mass of an object A to be 50.3 grams and measures the mass of object B to be 200.24 grams. She then reports a combined mass to be 251 grams. Is the student correct? Why or why not? Okay, so I forgot to write out why or why not and if they were correct. So make sure that you add that. So I'm going to add it. 50.3 grams plus 200.24 grams. And when you just straight add that, you get 250.54 grams. However, remember the addition and subtraction rules for significant figures. When you're adding 2 numbers, your answer must be to the precision of the number with the least precision. okay? So this one is precise to the 4. 50.3 is precise to the tenths. Therefore, your answer needs to be precise to the tenths because that's the number that had the least precision. So after I write this out, if this had been a 6, then my answer would be 250.6. If this number here had been a 6, I would round up. But it's a 4, so it's 250.4 grams, or 250.5 grams. Sorry about that. This is a 4, so you keep the 5. 250.5 grams. So was the student correct to report it as 251? No, because she did not report it to the correct precision. So you would need to show this, state this, and say the student is not correct because that is not, the answer is not to the correct precision. Okay? Number 11. What would be the units on the following calculations? You do not have to do the math, okay? So A, you're just adding centimeter and centimeter. That's just going to give you centimeter. B, you're just dividing grams by milliliter. So that's going to give you grams over milliliter. It's pretty simple. 12, which answer for question 11 will be a derived unit. That's going to be this one here, grams per milliliter. 13, what are the 2 basic rules for using scientific notation? Number 1, only 1 digit comes before the decimal point. You always show it so that there's 1 digit before the decimal point, whether it's 1 or 7 or whatever it is. 6.2 times 10 to the 3rd. Only 1 digit's going to come before your decimal point when you're using scientific notation. And 2, only significant figures go before the multiplication sign. So if I were to say 3.21 times 10 to the 3rd, that means there's 3 significant figures, the 3, the 2, and the 1 before the multiplication sign. So make sure your sig figs match there. Number 14, which is colder, 50.0 grams of water at 0.00 degrees Celsius or 50.0 grams of water at 32.00 degrees Fahrenheit? They're trying to trick you here, but 0.00 degrees Celsius is equivalent to 32.00 degrees Fahrenheit. So it's the same temperature. Which is colder? Neither is colder. They're the same temperature. Okay, now let's move on to the practice problems. Number 1, convert 2.4 milliliters into liters. So you're going to set up your factor labeling method, but you're going to put 2.4 milliliters over 1. And then I know that there are 1,000 milliliters in 1 liter. Again, if you wanted to say 1 milliliter equals 0.001 liter, that's fine. You're going to get the same answer. And I got 0.0024 liters. And then I'm going to check my significant figures. Here I have 2. Here I have 2. I'm good. Now, remember, when you're checking your significant figures, I'm only looking at what I started with in this problem, because the one that I used to do my converting factors, those are infinitely precise. This one, and this 1,000, because they're taken from measurements. So these are not included in your significant figures. It's just the numbers that you start with or the numbers that are given to you, okay? So 2 significant figures. Number 2, convert 69.00 kilometers into meters. So I have 69.00 kilometers. You set it over 1. And I know in 1 kilometer, there's 1,000 meters. And then I just multiply through. And here I didn't do it, but you just cross out your kilometers. And I get 69,000 meters. And then I look at my significant figures and I have I need 4 significant figures. The 0 comes to the right of the decimal at the end of the number, and this one will be between 2 significant figures. So I can, if I report the number like this, there's only 2 significant figures. So this answer would be incorrect. So I need to make it into scientific notation. Remember your rules, 1 digit before the decimal point and only significant figures before the multiplication sign. So it's 6.900 times 10 to the 4th meters. And that's 4 significant figures. And then if you were to multiply this out by 10, 1, 2, 3, 4, you can see that you get 69,000. Hopefully that makes sense for everybody. Let me know if it doesn't. Number 3. Okay. Convert 0.091 kilograms into cc's. Okay, so 0.091 kilograms over 1. And I know in 1 kilogram there's 1,000 grams. And then I know in 1 gram there's 100 centigrams, right? And then my kilograms cancel out, my grams cancel out, and I'm going to be left with centigrams, which is what I want. So then I multiply this through and I get 9,100. How many significant figures are here? 2. And how many significant figures do I need? 2. So I'm good. Problem number 4. If an object has a volume of 69.2 milliliters, how many kiloliters of space does it occupy? So 69.2 milliliters over 1, set up your factor. There are 1,000 milliliters in a liter. There are 1,000 liters in a kiloliter. And again, I just forgot to cross off my. And then that's going to give me 0.0000692 kiloliters. I need 3 significant figures. This is 3 significant figures. So I could just leave the answer like this and that's fine. But I'm going to go ahead and put it in scientific notation because I think it looks cleaner. So I'm going to do 6.92 times 10 to the negative 5th kiloliters. Remember, only 1 before the decimal. These are your significant figures. I need 3 of them. And then if I were to multiply this out by 10 to the 5th, I'd go 1, 2, 3, 4, 5. And you can see that that would match this. Okay, number 5. A box is measured to be 23 centimeters by 45 centimeters by 38 centimeters. What is its volume in cubic meters? So volume is going to be length times width times height of a box. So it's just going to be 23 centimeters times 45 centimeters times 38 centimeters. Remember, you're also multiplying your units. So not only do I do 23 times 45 times 38, and I get 39,000, I'm also doing centimeter times centimeter times centimeter, and I get cubic centimeter. Okay, so that's the first part of the problem, but it wants cubic meters. Okay, so I'm going to take my 39,000 cubic centimeters, and I'm going to say, what conversion do I know? Well, I know that 1 meter, there's 100 centimeters. So I'm going to write that down. And then I'm going to say, okay, well, I need this to be cubed, right? So I'm going to cube this conversion factor. And I'm going to show you that here instead of writing it like I did in the board in class. I'm going to show you here. So it's 39,000 cubic centimeters over 1. And my conversion factor is going to be 1 meter cubed, right? And then I'm going to do 100 times 100 times 100, which is the same as 1 times 10 to the 6 centimeters cubed. However you want to write that, it's fine. And then when I multiply that out and cancel my units, I get 0.039 meters cubed. How many significant figures do I want? I want 2. All of these have 2 significant figures. This has 2. I'm good. Okay, number 6. A nurse injects 71.0 cc's of medicine into a patient. How many liters is that? Well, this one, it's important to know this conversion. 1 cc equal 1 milliliter. So if the nurse injects 71.0 cc's, I know that that's 71.0 milliliters because it's a 1-to-1 ratio. So as long as you have this written here, you can just start with milliliters. So 71.0 milliliters, set up your conversion factor over 1. And then I know my relationship is for every 1 liter, there's 1,000 milliliters. Milliliters cancel out. So then 71.0 divided by 1,000, and I get 0.0710 liters. I want 3 significant figures. This is 3 significant figures, so we're good. Number 7, convert the following decimal numbers into scientific notation. Okay, remember the rules. You want 1 number before the decimal, and then only significant figures before the multiplication sign. So in this problem, 12.45000, everything's significant. This 0 is to the right of the decimal at the end of the number. Your 1, 2, 4, and 5 are significant, and then these numbers become significant because they're between the significant 0 and this 5. So every single one of these numbers needs to come before the multiplication sign, which is a lot, but so I'm going to move my decimal point 1 here, and I'm going to say 1.245000 times 10 to the first. Because all I would have to do to go from this number to this number is to multiply by 10 1, and you can see it's the same number. So this is how you would write that number in scientific notation. Okay, B. 3,040,000. Okay, how would I write this? How many of these are significant? Well, my 4 is significant, my 3 is significant, and this 0 in between them is significant. The rest are not. So I just need these 3 numbers to be in my scientific notation. So 3.04, because I only want 1 digit before, times 10 to the 6th. And you can see that if I 1, 2, 3, 4, 5, 6, I'd get the same number. C, 6,100.500. Okay, this decimal here is going to make this 0 significant. This 5 is significant, therefore this 0 is significant. This 5 is significant, this 1 is significant, therefore these 2 zeros are significant. You know that 6 is significant because it's a non-zero number. So every number here is significant. So I'm going to have 6.100500 times 10 to the 3rd. Because if I did 1, 2, 3, that's where the point is. Okay, D, moving on. 0.001234. How many significant? 1, 2, 3, 4. 4 are significant. These zeros are all not significant. So it's just going to be 1.234 times 10 to the negative 3rd. And if I were to 1, 2, 3, you can see I get the same number. Hopefully this is making sense to you. This does not make sense to you, please contact me. You can text me, you can call me, you can email me. I want this to make sense to you because we are going to be using conversion factors and scientific notation throughout this course, so you need to understand it. Okay, so moving on to 8. Convert the following numbers back into decimal. Okay, so now they're going backwards, okay? You're just gonna do the same exact thing that I was doing at the end of those problems, just showing you how it's the same thing. So if I have 6 times 10 to the 9th, I have 1 significant figure and that's it. So I do 6, and then you just go 1, 2, 3, 4, 5, 6, 7, 8, 9, and put all those zeros, and this is what you get, 6 billion. Okay, B, 3.0450 times 10 to the negative 3rd. You know that all of these are significant, so you're just gonna write these out without the decimal, and then you're gonna say, okay, the decimal would be here, so you're gonna go backwards and go 1, 2, 3, and add those zeros, and you get 0.0030450, right? 1, 2, 3. And then when you look at it, the only numbers that are significant in this are 1, 2, 3, 4, 5, and that matches up. Okay, for C, 1.56 times 10 to the 21st. Ooh, that's a big one. Okay, so you literally just go 1, 2, 3, 4, right, 21 times and add in the zeros, and here's your number. And I'm not going to attempt to say that number right now. D, 4.50000 times 10 to the negative 7. You know that every single one of these is significant. Okay, so I'm going to go backwards. 1, 2, 3, 4, 5, 6, 7, and then I'm going to have 0.00000450000. And if you were to look at what's significant, it's going to be all these, and that's correct. So you can kind of double check yourself after you get your answer by making sure it looks right. Okay, so for problem 9, convert 85.6 degrees Celsius into Fahrenheit. So I rearranged my formula so that I could solve for Fahrenheit. But just in case you don't see that, here's the formula they give you in the book. Degrees Celsius equals 5/9 times your degrees Fahrenheit minus 32, right? So if I multiply both sides, my degrees Celsius and this side of the equation, by 9/5, I'm going to get 9/5 degrees Celsius equal, my 9 and my 5 will cancel out. So then I'm just going to have degrees Fahrenheit minus 32. So then if I add 32 to this side, I'm just going to get degrees Fahrenheit. And then I'm going to get 9/5 degrees Celsius plus 32. Okay, hopefully you see that, but that's what I did right here. So I'm just going to plug it in. My degrees Fahrenheit is going to be 9/5 times 85.6 degrees Celsius. You're not going to keep that degrees Celsius. It just tells you what number goes into this formula to do the conversion. But I just put it there to be clear and show you. Plus 32. So when I multiply this fraction out and add 32, I get 186 degrees Fahrenheit. How many significant figures do I want? 3. That's 3. That's perfect. Okay. The temperature of the moon during its day is 396 Kelvin. What is that in Celsius? So I'm going to do my formula. Degrees Celsius equal Kelvin minus 273.15. So I'm going to take my Kelvin, I'm going to throw it in there. 396 minus 273.15, and I get 123 degrees Celsius. 11, the average low temperature of International Falls, Minnesota in January is negative 7.0 degrees Fahrenheit. What is that in degrees Celsius? So again, I'm going to take my formula, the one original. I'm going to plug in my negative 7.0 degrees Fahrenheit. I'm setting that there, but I'm not keeping it. It's just a conversion to show you. Minus 32. So when I subtract 32 from negative 7 and then multiply it by 5 and divide it by 9, I get negative 22 degrees. Okay, I hope that has been helpful for you guys for studying for your test.